In the earlier classes, you learnt that the temperature of a body is defined as its degree of coldness or hotness. We feel a body cold or hot because the temperature of the cold body is less than that of our body, and the temperature of a hot body is more than that of our body respectively. But this definition does not help us when it comes to measuring temperature. Let's conduct an experiment to understand this concept better. When a hot iron ball is dropped into a trough containing cold water, we observe the temperature of cold water increasing. Before we continue, let us define heat. Heat is defined as a form of energy that flows from a hot body to a cold body when they are in thermal contact. Heat is an energy that is in transit. Here, the heat flows from the iron ball to the cold water. When we touch a cold body, heat flows from our body to the cold body. If a hot body is touched, heat flows from the hot body to us. Coming back to the experiment, after a sufficient time, it is observed that the temperatures of the iron ball and cold water are the same. Now we say that both the bodies are in thermal equilibrium. When two bodies are in thermal equilibrium, there will be no net exchange of heat energy between them. For example, when a cup with hot tea is placed on a table, heat flows from the cup to surroundings until thermal equilibrium with the surroundings is attained. We define the temperature as a physical quantity that is same for two bodies which are in thermal equilibrium. That means when the teacup is in thermal equilibrium with the surroundings, it is at the same temperature as that of its surroundings. In SI system, heat is measured in joules and temperature is measured in Kelvin. We use a thermometer to measure the temperature of a body. While constructing a thermometer, we need to identify a specific property of a substance that varies linearly with the temperature. In case of a liquid thermometer, the length of the mercury column changes linearly with the change in temperature. Pressure of the gas in a constant volume gas thermometer and resistance of a platinum wire used in resistance thermometer changes linearly with the change in temperature. The temperature of a body can be written as a function of the selected property, say R. To assign a numerical temperature value to a particular length of mercury column in a mercury thermometer, we choose two reference points and assign arbitrary values to them. Among the two reference temperatures, one is considered the lower fixed point, LFP, at T1, which is the freezing point of water or ice point, and the other one is the upper fixed point, UFP, at T2, which is the boiling point of water or steam point. These two reference points used in many standard scales. In the Celsius scale, freezing and boiling points of water are taken as 0 degrees Celsius and 100 degrees Celsius respectively. In the Fahrenheit scale, they are taken as 32 degrees Fahrenheit and 212 degrees Fahrenheit respectively. If R1 and R2 are the values of the identified property, at the two reference temperatures T1 and T2, then temperature T when the property has a value of R is given by T equals to R minus R1 by R2 minus R1 into T2 minus T1. For a Celsius mercury thermometer, if the lengths of the mercury columns are L0 and L100, corresponding to two reference temperatures, T1 is equal to 0 degrees Celsius and T2 is equal to 100 degrees Celsius. Then the temperature T corresponding to a length of L is T is equal to L minus L0 by L100 minus L0 into 100. For any temperature scale, the ratio T minus T1 by T2 minus T1 is constant. This can be used to find relationships among different temperature scales. The relation between Celsius scale and Fahrenheit scales of temperature can be as shown. The same relation can be extended to find the corrected temperature shown by a thermometer which is calibrated incorrectly. If L dash is equal to LFP on a faulty thermometer, U dash is equal to UFP on a faulty thermometer, T dash is equal to temperature of the body read by the faulty thermometer, and L is equal to LFP on an accurate thermometer, U is equal to UFP on an accurate thermometer, T is equal to temperature of the body read by an accurate thermometer. Then the correct temperature of the body is found using the expression. Let's solve a problem based on this formula. The LFP and UFP of a faulty thermometer are minus 5 degrees Celsius and 110 degrees Celsius respectively. If the temperature of a body measured using this faulty thermometer is 45 degrees Celsius, then what is the correct temperature of the body? Here, T is equal to T degrees Celsius, L is equal to 0 degrees Celsius, U is equal to 100 degrees Celsius, T dash is equal to 45 degrees Celsius, L dash is equal to minus 5 degrees Celsius, U dash is equal to 110 degrees Celsius. Upon substituting the values in the equations and solving, we find that the actual temperature is 43.5 degrees Celsius. When a mercury thermometer and an alcohol thermometer are used to find the temperature of a substance, they may not show the same temperature readings. This is because the thermal properties of different substances are different, and the rate of expansion of a substance changes with temperature. That means the per degree expansion of a liquid is not uniform at all temperatures. The readings shown by different thermometers may coincide at calibration points, but may vary at other temperatures. Due to this, these thermometers are of no use when accurate measurement of temperature is needed. It is experimentally observed that the temperature readings of gas thermometers are independent of the gas used. Hence, these are more reliable for the accurate measurement of temperature. A gas thermometer works on the basis of variation in the pressure or volume with the temperature of the gas in it. Boyle's law states that if the temperature of a given mass of gas is constant, then its pressure is inversely proportional to its volume. At constant temperature T, PV is equal to constant, where P is the pressure of the gas and V is the volume of the gas. According to Charles' law, at constant pressure, the volume of a given mass of gas is directly proportional to its temperature T. Therefore, V by T is constant. On combining equations 1 and 2, we get PV by T is equal to constant. This is known as ideal gas law. PV is equal to mu RT is a generalized ideal gas equation, where mu is the number of moles of gas and R is 8.31 joule per mole per Kelvin, which is the universal gas constant. The constant volume gas thermometer works on the principle of the ideal gas law. Since PV is directly proportional to T, when the volume of a given sample of gas is constant, its pressure changes linearly with the temperature of the gas. When a graph is plotted between pressure and temperature, a straight line is obtained. If the density of the gas is low, the graph will be a perfect straight line for all gases